Hello, everybody. So, still just some odds and ends finishing out our time, things that will be useful. We hit all the major course learning objectives as far as what's on that list. And actually, we've done a little bit past what's on that list of course learning objectives already. And with the rest of our time, just like we've been doing, the lecture time will be fairly short, and that way there's plenty of time to work on projects, ask you homeworks, anything like that that might show up. Usually, as we approach the end of the semester, everybody has lots of stuff to do. So I have a couple odds and ends. I guess I'll start. I'll start with this. I have notes about that. Anything special is it? This was one I had in the yellow notes. So I like to talk about this every semester because there's lots of reasons to use this. And really, everything else on my list this evening is typing code. And this one I wanted to remind you about the Java docs. We can look stuff up, and we're just going to look at stuff this way. So something we might have to do commonly is handle output from our program. And sometimes our program is going to have a lot of output. In a classroom, we're under tight time constraints. So if we write a program that has 2 or 3 files, that's going to take all our time in the classroom. But in large industrial size settings, I'll use that phrase, we might have a lot more than 3 files output from the folder. A whole lot of things, and maybe they need transmitted across the network or put to a backup folder at the end of the day or something, where dealing with all those files is going to be a bit of a headache. Be a lot nicer if all of those files that our program outputs go to a zip folder and maybe add a little bit of compression so that it doesn't take extra room when it's in the zip format. And then we only have one zip folder to deal with. It's a lot easier to deal with. Well, Java includes a library for that. And there's nothing tricky about that library, so I was going to use that as the odds and ends reminder here about the Java docs. So it's in the util package. So Java util zip. We search for that. I was expecting Java docs right at the top. Okay, usually Java docs are right at the top. There we go. Docs.oracle.com. So back to the regular Java docs. So in the util package, there's this .zip, and there's nothing tricky about this. Everything's clearly named. We have multiple compression schemes. Obviously, they did not include every compression scheme, but some of our big ones. So we have gzip, and you'll notice it's a gzip input stream and a gzip output stream. For those who like 7-zip, 7-zip was an extension on that came long after gzip. Oh, I'm not sharing my screen. Sorry. Let me go back. Sorry, not sharing my screen. So let me go back a couple steps. When I first searched for it, java.util.zip, for some reason it only pulled up a bunch of tutorials. So I had to actually put the word documentation in there this time. Sorry, here's the stuff I was talking about. So there's multiple ways of compressing files and confirming we have stuff. So you notice there's checked input, checked sum, input and output stream, a gzip, input and output stream. A lot of people use 7-zip, which is an expansion of gzip. It came later and just some subtle improvements, and there's a lot of backward compatibility. If anybody uses 7-zip, you could give that a try and see if it works. There's a lot of compatibility with them, but I've never explicitly tried that myself. Just the regular zip. And you'll notice a whole bunch of them. Deflator, which is a pretty much the standard compression for just lots of text files. If you have other things like images and stuff that might need fancier compression, you might want to go to step up to gzip. But you'll notice they all have input and output stream. They all behave about basically the same. So like the gzip input stream, if we look at the constructor, takes in an input stream. So the same sort of input stream we use to write files and read files, those input output streams, those just feed into this other input output stream. You might remember that. We made a constructor of an object that had stream in or out stream in the name. And then the constructor for that took another object that had input or output stream. And that constructor took another object that took input or output stream. So it's more along that path. But it sends it to a zipped folder, which is nice because then if we have large collections of outputs and logs and data storage files and input files and output files and lots of stuff, we can compress it and like at the end of the day, send it to the backup drive with a compressed folder. A very useful one to have. So I wanted to point at it, and there's nothing tricky about it. Y'all can read through the docs. I figured I would use that one to remind you about the documentation. What I have in my notes? Oh, yeah. Also, one other thing that we haven't really talked about. So obviously, it's got its exception that we would expect, something called a zip exception, specifically made when we try to zip or unzip that folder. But notice there's also a date format exception. So along with that, this class, the zip folder always keeps track of when things were done. So when you go put your, well, it's a file, so it has to be in the try catch block. So if you're getting specific in the try catch block, it's not just the file and folder extension. We also have a date exception that could, the date could misfire on us. Then my notes say there is absolutely nothing tricky about this. The major classes are just names of the standard zipping methods with input or output string concatenated at the end. And a couple extra classes to deal with checksums. So everybody's seen checksums before. That's the super simple error handling. If we have a binary number, any binary number, I'll try going down at random. 1 0 0 1 1 0 0 1 1 0 1. Shows a completely random binary number. But just quickly looking at this, there are a couple things we can do. And one of those would be to count up all the ones, or some of the ones, but really that's counting them. So 1, 2, 3, 4, 5, 6. So we have 6 ones. And that gives us something that we can say definitively about our data. No matter how many bits we have, we can always add up the ones, and those are either going to come up to an even or an odd number. And that's the simplest type of error checking we can do, especially for like networks and stuff. So if we needed to transmit this across the network and we were worried about interference or something in the signal getting lost, a good way to check that would be add 1 extra bit to it, just as a sum. And I'll circle odd. So we establish in our protocol for transmitting it that all chunks of data will have an odd number of bits or an odd number of ones. Right? Our bit number is fixed, but some of them are zeros. So an odd number of ones. So in this case, 1, 2, 3, 4, 5, 6. That extra bit, we can just add that 1 in, make sure we have an odd number. Or if we had another piece of data, 1 0 0 1 0 1 0 0. I know it's a different size, but something here, 1 2 3, we have an odd number already, so that extra bit gets a 0 in it. And it's not a definitive check, because that checksum could be the bit that gets off. Right? Or if 2 bits get off, then we're back, we have the same parity. But it gives us a good rough estimate that something's obviously wrong with the data. And it is really, really easy to do. So that's the simplest sort of data checking. There's also, we have codes that can correct themselves automatically. Like TCP IP uses a checksum. So every bit that comes across the internet, anytime you've ever sat there and waited on a web page and little spinning things going and you're thinking it's taking longer than it should, it's probably something went wrong with the data in transmission. And TCP IP just has that checksum. So it counted up the bits and be like, nope, that should be an even number. You got an odd number of ones, send it again. Something wrong, send it again. But that's fine for the internet because sending an electrical signal or a light signal around the earth. In 2022, we have the combination of electrical cable and fiber optic cable. And that's no problem around Earth, but like that camera we sent to Pluto, when it was taking the pictures of Pluto, it was 4.5 hours each direction for the transmission of that data. So something went wrong, send it again would not cut it if we're talking about 9 hours to get that data back. That's way too big of a thing. So there are codes that can correct themselves. We might look at one at some point, but I like to show those in the SDEV 120 class or everybody. Just because it's an interesting thing and see some of the expansions of it and break away from that just integer representation. That's all we see in the lecture, right? Like this is how an integer is represented. And if you had me for the class or some other instructors, you might have heard a little addendum put on there. Like that this isn't how computers represent an integer. This is just the most basic format of binary code. It's not the binary code our machines actually operate on. Some people just bypass that little addendum altogether. If you're in C++ and say your data type is U int underscore something like 8 or U int underscore 16 or underscore 4, universal int, that's the one you would have learned about. That's the one the lectures cover. If we have a regular int, it is not that simplified version of binary that you learn. Just sort of introducing binary. Just in case you were in a class that didn't have the little addendum on there. And then there's other little differences, right? We know for certain the Python programming language has 32-bit integers. But if you check the size of a Python integer, it's using 128 bits, not 32. So that 32-bit integer is just a little piece of the data. It's not the whole thing. But a checksum is our simplest way. It's a really easy thing. So hopefully you can see immediately that it's not hard to figure out whether we have an even or odd number of ones in whatever binary code we get. So we see those quite a bit, especially in places where things can be repeated. We can just see that, check that before we close the software. Right? It's like, okay, write this zip folder to this our backup drive, and before we close the software, we can do the checksum and be like, oh wait, there should be an odd number of bits in that and in that. So if something went wrong, try it again and keep checking it that way. But nice, that's one that there are lots of reasons why a zip folder might show up for you. And I'm going to make sure and remind you about the Java docs. Y'all know about those. Java docs are very, very thorough, cover everything. We generate those websites from comments. I've been seeing it in several people's homework throughout. NetBeans tries to put it there automatically. It's just a multi-line comment with an extra asterisk at the beginning, and it generates that entire website. In NetBeans, just because it's been a minute, if you forgot, I don't think we wrote any in here the other day, but you right click on the project name, and then there's the generate Java doc to actually create your Java docs, which when we're talking about odds and ends, that was at the beginning of the semester, and that's a useful one. So let's look at that real quick on the 2 classes we wrote the other day. That way, that won't take very long. So we have this class thread and add the Java docs. I'll just start a multi-line comment with 2 asterisks, asterisks, whatever the plural of that is, multiple, yeah, stars. In math, I'm a math person, we usually call that, in math, we just say star. It's a much easier word to deal with. So a multi-line comment with 2 stars, like who wrote it, thread, so this was the thread, so an in-class example of inheriting from the thread class in Java for multi-thread. And it is generated in a website. So basically you can put HTML code in there if you want to make your website look a little bit better. Things like bold and italic. I wouldn't go crazy with the website with the HTML, but some of the simple things, bold and italic, or suddenly make something bigger or smaller. Some of the little tags can be really, really useful at times. Then it says who wrote it. When we come down to the constructor and add another one of those comments in. So one arg constructor to describe this, and parameter is name. Or there's a parameter called name, and this is the name of this object of an instance of this class. Probably easiest to track if we use the same as the variable name. So kind of like a tag. I guess all I really did there was describe what a tag is. Could have summed that up with 3 letters, and most programmers would have known immediately what I was talking about. But I didn't realize that till I was almost finished with the sentence. But just a description of what the method is, and then what the parameters that are needed for it are. Same thing on this next one. There's no parameters. The method that gets split into multiple threads. I guess that's all of that one. And unrunnable. Put a name there, and then an in-class example of, what was this doing? Using the runnable interface for multi-threading. I think I spelled multi-threading wrong, but not a big deal here. One arg constructor, and name is the reference value, I'll say a reference value for this object to identify it in the output. Here we had a couple methods. So run again is, well, same thing I put over here for the run method. So I'm just going to copy this. And then this one, the start method is method to actually configure and initialize a thread or multi-thread. Zoom pictures get in the way. There we go. And once we get all those in there and save it, I guess I'll do a couple things here real quick. Which one was that? So here you'll notice we have the build, the NB project, so NetBeans project, that has our build information. The different things we need to generate the manifest. I mean, an AMP project generates the manifest that runtime looks through and checks what all's imported and puts together a file so other things would know that. And this NetBeans NB for NetBeans project that has all the information to generate that and other things for working with it here in NetBeans, the source, the test cases, since we did use the profile button the other day. But whenever things are working, something we haven't done, we haven't really clicked the build button. Let me clean the project. Make sure it's all the empties all the caches and everything that I had. And then hit build. And now we have this distribution folder, DIST. And you'll see in there is this single jar file. A jar file is the equivalent to the Java virtual machine equivalent of like an exe, an executable file for Windows. So that's the final version of it, the final product ready to run. So if you remember right before, I think it was right before Thanksgiving, we spent a night looking at them. You don't want to give that to your users directly. Write a batch script or some sort of script that checks to make sure all your resources are in order. And if you need something on the internet, make sure you're connected to the Wi-Fi and confirm all of that stuff, and then start it and let your users start that. And then that script starts this one. And then building installers, we saw all that. But that's the distribution folder, the final version. And if we right click on the project name again and generate Java docs, we went ahead and opened them. Oh, actually, I'll close it and go in back in that folder. You notice now there's a folder in there called Java doc. And somewhere in the top level of that, we should have the index. Yeah. So here's all that. You want to put that documentation together on everything you do. Because doing it in the comments also makes it a lot easier, because then you can just put that comment in whenever you're at the method. Which hopefully that makes sense for, like, say, user manual. If we use that terminology for documents. The best time to write the sentence in the user manual telling somebody how to use your code is as soon as you finish debugging it, because it's fresh on your mind. And so you finish your method and then just throw the Java doc comment in top of it. And the best part of that is you don't finish the fun part, the coding, and only have the boring part left. Yeah, I remember learning that the hard way, and I'm sure y'all are probably going to learn it the hard way yourself one of these days. You'll sit down and start coding, be all excited, and get some great project together, and then realize you need documentation after you finish all the fun part. Then there's no fun. Then there's nothing fun left in it. It's just writing, putting together all the documentation, the boring stuff. So it works. You don't want to run out of fun part and only have the boring. So here we have our Java docs, which extends runnable. So if I click this, notice we're back to the docs.oracle.com. So it even includes links to all the other Java docs. They all link together automatically. So you want to work those into your programs along the way. It's a lot easier to get the documentation done when it's just a comment that you put in there. as you write the methods, because it's still just as boring if you have all the code finished. And all you have to do is go through all of your objects and add any comments. That's not a fun part. There's some stuff about that. If we should look at the thing that's on the homework, the next homework assignment is this weekend is a time you are likely to work on that. It's fairly straightforward. Do I have any fancy notes about streams? Oh, streams. There's only half page of notes, so apparently they didn't do much on the notes. Let's see. It's in chapter 30 of the textbook. Was everybody able to access chapter 32? Chapter 32 was also this week. Okay. I just remembered that I downloaded another copy of that. I never uploaded the new copy I downloaded of that. But if the website, Pearson website goes down again like it did the last time we had to get some of the extra chapters and we can't get to it, I do have one on there. I'll put it on after the lecture tonight. I'll put a link to it or add it in an announcement. See some data structures and processing capabilities built into them. And there's a lot of different things we might want to happen. So the idea of streams in particular, really we want to call this a collection stream, different than an in-out stream, but an in-out stream would be similar, just closer to the machine level. It's doing the same thing, but instead of a collection of data, like a collection of strings and integers forming maps, and then using that collection to process a whole bunch of things at once, the in-out streams would be more like a collection of bits, because it's the actual transferring to something else that needs the pure binary code. So processing abilities that are combined in one package and clean themselves up afterwards. So there's a bunch of preset methods we can use along with lambda expressions and put all of the stuff we need to do for processing a collection into one line. So it's just spreading it out a long ways. It's one line of some pre-built methods. We can also build our own methods. One line of method calls right after one after another in a certain order, so that yeah, they're all method calls, so it's not a very long line. It doesn't look bad, and we get a lot of our processing done in one single line. So let's look at an example of this. I'll create a new project. I'll just do a new project, that's fine. I'll call it stream, collection streams. Internally, the workings of an in-out stream, which would be the one that video streaming is named after, or video game streaming is named after. Oh, let's mention video games. That might be a good time to ask this question. One of the things on my notes tonight, I know there's at least 2 people in here that have taken or are taking the game dev classes right now. And at least one other person has mentioned that. So for the odds and ends next week, would you all like to take a quick look at the game engine? One of my favorite game engines to use is involves it's written in Java. I see a head nod here in the classroom. Anybody on the Zoom call paying attention? Can give a thumbs up or something. There's a game engine called JMonkey. It's one of my favorite ones to look at. So if anybody's interested in game stuff, we can look at that. It's primarily for PC gaming, but it does have Android output, which would include the current virtual VR standards. Those are just Android devices, and a couple others. I don't think it has PlayStation or Xbox Unity. But it's a really nice engine to work with. I think a head nod here in the class. Don't hear anything from the Zoom call. So, I don't know if anybody's paying attention or anything. That was one of the thoughts for next week. But I was going to check on feedback. If y'all wanted to take a look at a game engine. They might not be listening right now. But either way, let me know if you want to look at that. I'd like to see more than one vote before I switch to something big like that, because it will take a large, well, it took an hour and 5 minutes to put the YouTube tutorials together. So it'll take basically the whole class one night next week to look at that for the starting point. Oh, there's something in the chat room. Indifferent. Okay, so I know some of y'all's interest in things, so I try to keep that in consideration. And I know that several people have looked at different, several people have taken game dev class like games, and at least one other person has mentioned it. Multiple people wanted to do games for their final projects. So, oh wait, actually there's 3 people, Bradley's in game dev too, isn't he? He's not here tonight, so yeah, we might look at that. It's one of my favorite game engines to work in. They have excellent Java docs. Like their Java doc, there's not a lot of tutorials online. That's why I went ahead and made tutorials, because it was one of the ones that it was hard to find tutorials for it. So I just figured out how to use it and made some tutorials as a place to post some ads. Like not clickbait heavy, but a couple ads on a web page, and there's not many tutorials about so people that want to learn it can find a tutorial, and I get a few cents every time somebody looks at that tutorial. Seems like a good place to post ads. But it does happen to be one of my favorite game engines to work with, possibly because I really, really like Java. Some of the really liking Java programming is that I've done more stuff in Java than any other programming language. When I'm typing in another language and drift off and start typing learning syntax, it's usually Java syntax that I'm typing. But the way the engine is put together, like reading through the source code, figure out what to put in the tutorials and stuff, it was in the Java docs. It almost made me wonder if it was somebody's like graduate thesis from a computer science degree somewhere, because it is like the perfect example of the Java naming conventions and what Java docs should look like. But that's the doc. So it has great documentation, but it doesn't have like lots of YouTube tutorials, and it doesn't have lots of there's virtually nothing about it on YouTube. That's why I thought it would be a good place to post some ads. But that's a different point. We might look at that next week. It's also NetBeans is open source. So when they made the game engine, they downloaded the source code of NetBeans and extended that into a game engine. So a lot of the stuff y'all are probably already familiar with from using NetBeans also that's good. So that might not be a bad one to look at and see some, see if you like it, or to fill the space. Now collection streams. I was gonna do it in the main method here. So we need 2, well, really we just need 1. Actually, we need 2 packages. I was trying to think of how to word that. So I'm going to import java.util, and I'm going to do asterisks. But what we need from the asterisks are our collections. We saw those first few days data structures. Linked list and array list, stacks, queues, priority queues, maps, hash trees, binary search trees are in there. We talked about that. Like we needed to make our own as if it wasn't already included in a language that's been around for 30 years. All of our collections are in the java.util package. And that's a folder, right? If you're not used to seeing it, folders, directories, and files are object stuff. So there's a folder called Java, and in that is a folder called util, and in that is a whole bunch of Java files. That's what that notation really means. But since we are in code right now, we don't need it in the address we don't need it in the normal address form, we need it in the object-oriented form. So a folder is a child of, or a subset of the object it's inside of. Nested objects, I guess, would be the best way to say that. Same thing with files. But it's not just files. It's not just a bunch of .java files or maybe compiled .java classes in that folder. There's also other folders. One of those is java.util.string. And I'll just go ahead and import everything from that folder. And this is the one we're going to look at. It gives us a bunch of methods to make things easier to work with. I'll just use a set. Remember, a set was our basic collection, right? That's like a set in math class where you just have curly braces and a bunch of things in there. There's no index. Anything we do in a classroom, it would probably never show up in a classroom, but we can't count on order. The computer's going to choose the order for the set. So it might give, if we put a bunch of numbers in there, 1 through 10, it wouldn't never do this on 1 through 10. But 1 through 10, it would give them back to us in the same order we put them in. But hypothetically, we could put that in there, and the computer might give us 2, 4, 6, 8, 1, 3, 5, 7, and then 10. So, and then the next time we do it, the computer might give us, if we say loop do it, the computer might go 10, 9, 8, 7, 6, 5, 4, 3, 2, 1. It wouldn't do that until our data set got much bigger than 10 elements, but that would be hard to describe quickly. But hopefully that makes sense. We just have this collection of things and there's no order to it. They're just all connected. So I'll just do some integers for our example here. A set of integers, I'll call it my set, and let's use a hash set. So it's hashed. It's not all the way to a hash table. It's still a set over in RAM, but it is hashed. So it's much more, it's better than if it was just connected like a list or something, like list are connected entirely in RAM. We're getting close to that ideal that we get from a hash table where what we see in code and draw pictures when we're talking about it is essentially what happens when we, as far as the electricity going in and out of our RAM chip. So a hash table is ideal. We're not quite there. It's really close if we do a hash set, but it is still a set. So it's still entirely in RAM. And I'll just put some random things there for I start at 0. I is less than 234. Sounds like a good number. We'll probably go bigger than that. Let's go 1, 2, 3, 4. That way we got a decent sized set to work with. Larger than our typical classroom examples. And this is just going to be a random numbers. My set. Math.random times 99. Except it needs to be an integer. There's ways to pull up the random number, right? You can import the random package and have a whole bunch of things. If we just go to the random math library that's there by default, that's the probability when the number somewhere between 0 and 1. Multiply that by 99, and then we have a number somewhere between 0 and. Actually, I guess we could multiply by 100, couldn't we? Multiply by 100 because it 0 and 1 includes 0 but not 1. So multiply by 100, and then we have a number somewhere between 0 and 99.9999999. So if we knock off the decimal part, we have that a number somewhere between 0 and 99. Have we seen this? Is that strictly for arrays? What am I thinking of? Oh, that would be an array. I was thinking of something for arrays. Should be able to print that out and see what we get there. A whole bunch of numbers. 0, that's not right. My set for each, and I'll do this as here's a lambda would work. For each, I'll do the other for each loop. So for each integer I in my set, print out I. Oh, wait, I don't need each here, do I? There we go. This is only doing one thing. Um, wrong spot. Does anybody see whatever I'm not seeing here? Okay. I guess I needed extra parentheses there. I thought it was doing this first and then casting it to an integer. But apparently it was casting this into an integer, which always gives a 0, and then multiplying that by 100 and ace. Does anybody know remember what our one condition on a set is? What our restriction is? It kind of stands out there. We put in 1,234 zeros. Let me go back to that little error. If we put in 1,234 zeros, we get 1 0. So a set does have the restriction no duplicates. I'm gonna put those parentheses back in there, and then we should be able to print that out. My set. Now that we have some non-duplicated numbers, I don't know why. My mind was just elsewhere. I have no idea why I said 1,000 non-duplicated numbers and only gave it 100, 0 through 99. That's definitely not going to give us 1,000 non-duplicated numbers. So I'm going to change that to 25, which is what I have in my example. I should have stuck with what I had in the example from when I was getting ready. I did 25 there, and then suddenly decided to change that to 1,000. So there's 25 numbers, random numbers. Probably be nice to do some stuff with it, right? We might want to put them in order, figure out which ones are larger, smaller, lots of different things. There's a list of things in the book, and it's an active subject we learn by doing, so we're just gonna look at the basic syntax of it. So another thing we can do with that set is we can say my set dot stream, And that's our initialization. There's 3 parts to a string. Initialize the string. Then we have some mid-range things where we do all of our processing, and then a final thing. And the final is like outputs or copy it over into a new set. So we have that filter version. So let's start with limiting. So string dot, and we have, you can think of it like filters. So match, you'll see that in there, the text, some collections, distinct things, which we're in a set, so we already have distinct. Distinct was drop while, we can set up some condition and just remove it from the list. Filter is useful. Limiting. So maybe we don't need all of our data. We want to do it in small chunks, essentially building a buffer along the way. Build our own little buffer, so we'll only do a few at a time. You can remap it. A whole bunch of things. Reduce it. Skip so far ahead so that if we limit it to like a buffer, we limit it to 8 at a time, then on subsequent passes, we can skip 8 ahead every time because we just got rid of the 8. Or we do it in a loop, right? So from 0 to, I don't know if we had 64 things, 0 to 8, we're going to do 8 at a time, so limit it to 8. And then on the next pass, we limit it to 8 plus, or 8 times 1, because we're on the second round of the loop. Then 8 times 2, 8 times 3, 8 times 4. We limit it, and then we can also skip ahead that amount so that we're looking at the next bit. But different things about filtering. Again, take while, so sort of looping through things, turn it into a list. I'll start with limit, let's say 8, so that's on my mind. So describe our stream, let's limit it to 8 values, and then we'll filter them. And notice what the predictive text wants to put in for filter, a predicate. We really seen that word anywhere? This is a link. If we click it, we get the Java docs. A Boolean valued function whose method is something, the type of input to the predicate. It's not the way we would normally use predicate. Every once in a while, it shows up in very formal language, right? Like you being the +1 on the RSVP to your significant other's cousin's wedding is predicated on you still being your significant other at the time of your cousin's wedding. Or in other words, or in normal English, if you break up before their cousin's wedding, they're not going to take you to their cousin's wedding. That makes sense. So a word we only use in very, very formal English is predicated. So we want the data, we only want to include the data predicated to some criteria, predicated on some criteria, which is a lambda function. So it has to satisfy this lambda function, a lambda function that we'll put in. So it's based on an integer, so and then our lambda arrow. I always want to say arrow because everybody except the Java developers thought that was an arrow, and they thought it looked like the Greek letter. But our I is less than 60. So we'll take the first 8 items predicated on the fact that that item is less than 60. We don't want any numbers bigger than 60 there. They used a very formal term. Usually the words that were chosen are less formal than predicate. And when we use that word in English, we only use it in past tense. Right? The way I just said that sentence, the first 8 items predicated on the fact that that item is less than 60. Our first 8 integers predicated on the fact. It only comes in past tense. So the fact they use predicate for that, I guess it's still an object for that class seems a little strange, but and then we can do something to wrap it up. So stream initializes. Then we have the middle range, which limit to 8 and filter on that condition with the big fancy formal sounding word. And then we need to wrap it up. So maybe do the for each. And this is the for each my set dot for each. We did see that earlier, but it works a lot. This is what we didn't spend much time on it earlier because it usually goes in something like this at the end of a string. And then after we do that, then I guess we can output them. That sounds like a good thing to do. I guess that shortcut doesn't work inside of a thing. Print Zoom stuff's in the way. Float. Sorry, for each is a lambda, another thing where we need a lambda. I remember typing the lambda and I recently and forgot I need another one. So a lambda function is local. Excuse me for the coughing. I've got a cough drop in my pocket. I should put one in my mouth. So our lambda function is local. It only exists in that function. So then when we get to the next function, we need another I. So for each I, then work there. Print out I. Let me expand that so it fits on the. Oh, that line fits on the screen, kind of. And see how we do all of our filtering in one line, and it's all method calls, so it's not a very long line. And with the lambdas, it doesn't get super confusing because we never need any curly braces in there. Before those were brought into Java around 2014 or so. There might have been some beta test earlier than that. But before that, this was a mess to do because we needed curly braces. We'd have to instantiate what lambda took the place of and then put that in there, which was an object. We'd need objects with curly braces, and it used to be a large mess. The lambda functions cleaned that up a lot. So if we run that, so we can see the original list and try printing I without quote marks on it, and then put a comma afterwards. There we go. So you can see it went through our list. The first item was 65, which does not fit our predicate. So that one's ignored. The next one, 2, 3, those are good. 99. Oh, 99 does not fit our predicate. So discard that. 35, 37, and we filtered it down to the first 8 elements that were smaller than 60. So hopefully you can already see some use of that if that's extended out. Lots of filtering properties. We don't necessarily need to sort our data. We don't care what order it is. Those happen to be in order, but that's just coincidence from how it ran through the set. it was random numbers, so if we run it again, okay, those are clearly not in order. We get the same thing. We don't need to worry about sorting them or anything. We're just doing that. I guess in a more realistic situation, you wouldn't be printing it out. You'd be adding it to a new array. You'd be adding it to an array that had 8 elements. And then those are the 8 you need, just the first 8. And little things like that. What else do I have in the example? Maybe all of the elements less than 60. So my set dot, again, initialize it with stream, so that one always goes first. Let's apply the same filter this time. So filter lambda, our lambda function with a parameter using I as the parameter in the lambda function, and I less than 60 to set up our parameter. And then to do math with things, we want to use dot the reduce. So you can see it's overloaded. And that's an object we haven't really talked about, but binary operator, you know what an operator is. Right? Addition, subtraction, multiplication, division, and or not. Some sort of operator that we have to feed into the accumulator. They call it accumulators, it's an actual piece of the CPU where we would add a bunch of things together. So to do math, we want to use reduce and then set up a lambda function here. So say an accumulator, we want the sum. Remind you what we were doing here. Find sum of all elements less than n. So we're going to start at 0. Starting point at 0, and then we want to take 2 elements, so we have a double lambda this time. We have 2 parameters for our lambda function, a and b, and they're both getting fed into the lambda function. That's why they get the parentheses. So if you need 6 parameters, wrap them in parentheses and comma separate them, follow it with lambda. And I guess it looks more like a function this way because we have parentheses. And notice how it's a function that's read backwards. So we have parameters and then the function name with the lambda. It made sense in 1959 when they created that in the Lisp programming language. If anybody's used Lisp, that would make more sense because Lisp goes in machine order. So if we need to add 2 numbers, we would put plus 75. We don't write it in human form, it goes in machine form. Same thing with functions. We need the parameters we're sending in, and then we need to know where we're sending them. The machine can't know, when the machine sees where to send them, it has to already know what the parameters are. So just like adding, the machine can't see before a machine can add 2 numbers, it has to know it's doing a binary operation. Because some of our math operations take 3 numbers, or some take 1 number. So it has to know how many numbers would follow it. So the operation goes first. But with the function, it's the opposite. We're sending parameters to a function. So the machine needs to know which parameters are getting sent before it knows where to send them. That's why the order looks backwards, but that's opposite from how the human mind works, which is how we normally write our functions, right? With function name and then the parameters. I guess the words to and with would make sense. So a lambda function is these parameters to something, and a function like we're used to is a function with these parameters. Just in case you were wondering why it was a function of them. I should finish that out. We're gonna add them. I already said we're adding them, but y'all might not have known to type that directly. And reduce is a final operation, so I don't think this is gonna work. I'm gonna copy that. I'm pretty sure I need to wrap the whole thing. Oh. Yeah. So reduce is the final thing. Reduce is like printing it out. We get to that last method. So initialize all the middle stuff. We have lots and lots of middle stuff, but then we can only have one in. Okay. We already finished by finding that sum, so we can't continue on and print afterwards. So I'll just wrap this whole thing in print. Put a parenthesis at the end, and then do the system.out.print line. Oh, probably need to print a line break before we get there. It did it. It just put them on the. It just put it on the previous line. There we go. See how we didn't address that last comma, so there was no line break on the end. So it gives us the sum of everything less than 60 there, which with random numbers can be different, but we could sum up everything less than 75 just by changing that number. All of those is maybe one we could add up in our heads. Sum of everything less than 10. That way we have a bunch of numbers we can add up in our head. 0, and I don't see anything less than 10 on that list. But if we run it again, okay, I've got a 5. There's only one thing to add. Okay, here we got a couple of them. So there's a 3 and a 5 would be 8 plus 6 brings us up to 14 plus 7 is 21. And I don't see any other single digit numbers. But it gives us a way to quickly work through our data set, not just sort it and organize it. We can do a lot of processing with lambda functions. And those two right there, those three right there are probably, there's more, but those three right there are 99.99999. Everything everyone want to do with strings. You're going to want to limit them, filter them, and do some math with them. There's another thing that we need streams for. One, which I guess will kind of finish out tonight's thing. This is how we normally take an example, but I want to type these last two lines because the other day we were talking about multi-threading. We split our program up and to multiple threads and let the CPU jump back and forth and decide how to run each particular instruction so that from a human perspective, it looks like they're all running at the same time. When I said that sentence, I said the CPU, one of them. How many people are on a machine that only has one CPU on it? Your phone's going to have at least 4, right? I'm on the laptop here. The one the screen share is from is from the cheapest laptop they sell. The cheapest laptop they sell at Walmart that has Windows on it. If I pull up the system, oh, I was expecting the number there. Maybe I need to look at Device Manager. very few machines only have one CPU, right? Oh, processors, 1, 2, 3, 4. So the cheapest laptop at a store known for selling cheap generic things is going to have 4 processors on it. So it'd be nice if we could take advantage of all 4 of those. And in a lot of languages, we can do that directly. But if you remember, Java was one of the first successful attempts to make write once, run anywhere code. That's pretty standard nowadays. If the language doesn't do that, we hardly do. But Java was one of the first ones to do that. And they did so by creating a virtual machine. So this machine might have 4 cores on it, but the Java virtual machine does not have 4 cores. But it can still take advantage of them with streams. So if you want to take advantage of parallel processing, which you would probably want to do when you have lots of data to work through. Right? There's no point in doing that if you don't have hardly any data. It would take longer to split it up and send it to different cores than it takes to get through all of the data if there's not much. So for large collections of data, that's when we would want to do that. So this is where we get parallel processing here. Let's say find the sum of the list using parallel processing. Parallel processors. Another one that was left off of the objectives list, and I really don't understand why they leave that off the objectives list. In all of the SDEV classes, it's like you're not going to find a machine with a single processor. Why is parallel processing not on the major course learning objectives? Because we have to explicitly develop our program to be run on parallel processing. But for Java, we do it with the streams here. And I guess first off, we'll grab what we can get. So I can't think of a good lead in. We need the runtime. It's a static object. Y'all have heard runtime used as a verb, right? We will do that at runtime. We'll figure out what our input is at runtime. Runtime is also a class so that we can access all that stuff that happens at runtime. We'll see our error messages at runtime. Right? We'll instead of digging through a big messy text file, we'll just hit run and see if there's a typo from the error messages that pop up in the console. It's a lot easier to find that way. Right? If you have 500 lines to dig through, and you're not sure if there's a typo or not, and hit run, it'll tell you exactly where the typo's at runtime. So we can access that from a class, and it's a static class because there's only one runtime. We don't have multiple runtimes. And from it, we can then get our runtime. That seems a bit redundant. That's why I couldn't think of a good lead in. So I can talk about runtime. Everybody talk about that, but then, yeah, it's runtime.getRuntime. It seems redundant to me, but I didn't write that line of code. And from that, we can ask for available processors. Which again, I should probably print this out so that we know what it is. So I can come back to the beginning and system.out.println. So you can see here our master machine got 4 processors. So we can do a lot better than passing those numbers to one processor. We'd already measured in nanoscale, so we're not going to notice it on this list. But when you have a list with millions of numbers, change that to a linked list, like later after we write the next line. One more line of code to write tonight. I know it's coming on that. It's been over an hour, but one more line of code. And when you're doing your own thing, try changing this to a linked list so that you can have 10,000 random numbers between 0 and 99 in it. And then you can, well, if you went, actually you can get bigger than that. If you went with 1 million items, you probably notice it and you can summing all of them together versus all of them together on parallel processing. But once again, it's a stream. We access that from streaming. And our middle one, and in that mid-range, the active stuff, initialize it, all of the doing stuff, the activities, and then the finalize. There's different words we could use there, but 3 parts, and almost all of it happens in the middle. One beginning, one end, everything in the middle. So our first middle is do this on parallel processing. Just the word parallel. And I'll just add all of them again. I'll skip the filter this time. Reduce on an accumulator, start at 0, pass the parameters A and B into a lambda function that just finds the value of A plus B. Oh, and then I need to print that, but because again, reduce is a final step, so we can't do a second final step. We only get one final step. That's what final means. So with a short list like this, there's no possible way we would be able to see the difference. But give that a try at lab when you're actively doing stuff in lab time. And by 10 million items in the list, you would definitely see it in human time scales. Right? Nanoseconds are a millionth of a second. So if we're measuring things in millionths of a second, when we get up to millions of things, we're up to seconds. But we definitely won't see it on 25 things, not on modern computers running on 4 processors. So if you just did that line with and without the parallel and had it switch that set to a linked list so that you could have duplicates, you would probably notice that you would notice the difference. Or it might be good to just increase the size of how many random numbers are there until you see the spot where you notice the difference. That's an important one, I think, not on our stuff, but we need streams to do stuff in parallel, which makes sense because we're not going to worry about, oh, we need to use lots of cores in order to get this done quickly until we have lots of data to go through. And that's what streams are for. Does anybody have any questions about that? See a head shaking no in here. Okay, I assume 5 seconds of silence means no questions. So that was an hour and a half, leaves us an hour and 20 minutes. Actually, that was, yeah, we're a little bit past halfway. We're 3 minutes past halfway, which leaves us plenty of time to do stuff. It's an active subject we learn by doing. And at the end of week 7, I can pretty much guarantee that you all have stuff to do this evening, right? So I want to make sure there's plenty of time to do things. 5 seconds of silence. I assume nobody had any questions. So that'll be it for this evening. And I have one vote, so one kind of head shake and one indifferent for the game engine lab. So I don't know if that's really enough votes to spend a whole evening looking at the game engine. There's lots of other things we can talk about, but if you're interested in seeing a game engine, a very powerful game engine with a really, really nice rendering pipeline written in Java, let me know, and I can include it next week. Otherwise, I have other things that I can include next week. The Java programming language is huge. We're barely scratching the surface of it in one class. Otherwise, y'all have a great weekend. If you have any questions, let me know. I will see you all on Tuesday. Oh, and remember to register. We had that vision. Register sooner rather than later.